And it's my great pleasure to introduce Professor Bjorn Engquist from the Department of Mathematics at the University of Texas, Austin. And Professor Engquist received his Ph.D. in numerical analysis from the University of Uppsala in 1975. And in 2001, he moved from UCLA to Princeton, where he served as the director of the program in applied and computational mathematics. He was also professor and director of the Parallel and Scientific Computing Institute at the Royal Institute of Technology in Stockholm. In 2004, Professor Engquist moved to the University of Texas, where he's the director of the Center for Numerical Analysis. And Professor Engquist is a member of many academies of science, the Royal Swedish Academy of Science, the Royal Swedish Academy of Engineering Science, the Norwegian Academy of Science and Letters, and the American Academy of Arts and Science. He was awarded numerous prizes, the first prize, Siam Prize in Scientific Computing in 1982, the Peter Henrici Prize in 2011, the AMS Siam Birkhoff Prize in Applied Mathematics in 2012, and the most recent is the Siam Pioneer Prize in 2015. And we are very happy to have you here.
Thank you. It's great to be here. So I'll talk here about sort of a framework that we have to work at. It's not so much a method, but a framework to do multiscale modeling. And so I'll discuss a little bit the challenges from multiscale computation and how to couple models of different scale, and then discuss a little bit more details of this particular approach and see some of the applications that we have looked at in order to that. So we have many physical processes where, of course, interaction happens or on different scales. So if you take this just flying an airplane here, it's of course the scale of this overall systems, which could be the air around the air, hundreds of meters. And then you can look into the turbulence, which has a large range of scales, down to the smallest eddies that is around the airfoil. And you could look at the individual processes. That, of course, is coming from molecular action. And molecular action might even be more important in the modeling if you are looking at the combustion processes and see pollutants, etc. So typically, the ideal setting is if you can isolate one range of scale that you're interested in and doesn't interact too much with the other. So you can find a model that is fine for an individual scale. So that could range then from the atomistic part in quantum mechanics all the way to via Navier-Stokes, and that could also be too challenging for computational purpose, so you have to approximate that by some turbulence model. So that is the ideal setting. So we will then look at situations where it is this is not valid in a sense. So we do have something where it should be better appropriate to deal with a wider range of scale, or even deal with different types of models. So the heterogeneous here means that we could be in a setting where it is not the same model for the scales. As you would do Navier-Stokes turbulence, you have the same Navier-Stokes everywhere. You have Maxwell's equation for long and short wavelength, even if they interact. But sometimes you use different models, so that depends on the setting. So, it is not possible you can take this example here. It doesn't work so well to illustrate with a cup where you cannot look through. But the idea here is that if you would simulate the air, the water around in the container of a glass, then Navier-Stokes condition with the appropriate boundary conditions and surface conditions would be very adequate formulation. So you can live on the continuum scale over here. Until you tilt the glass. Then, of course, the no-slip condition is not valid any longer. You actually, in this case, the coffee would slide up along the boundary, so the liquid here, right around the slip line, is not stationary in this case. So, you would then need to either have some ad hoc engineering approximation of that, which is fine and works usually very good in this case where you know so much about it. about the angle and how much it slips depending on what happens in the fluid. But if you would like to do it in a more careful way, then you would actually go down and have the continuum for most of the fluid and go down into molecular formulation close to the slip line. Because the molecules actually move there. They are stuck for the other part here at the boundary, but there they actually move. So this would be a case from everyday life. It's obvious to see that it would be nice if you could couple them together. The challenge is basically coming from the fact, of course, the simple argument here, that if you have a certain size and you would like to describe functions or processes that vary a lot within that. So you think about particularly if you decompose it into frequencies, and then the smallest wavelength is much smaller than the larger domain. Just by information theory, in order to just represent it, not even solving it, representing it, you need epsilon, 1 over epsilon to the power d number of components, whether these are modes or whether these are grid points in the discrete method. It doesn't matter in this case. And this is a big thing. So if now epsilon, if you have a phenomenon that on one hand describes things on molecular level, or on the other is on systematic level, you can, the overall system must be extremely small so that this doesn't kill you in terms of memory. And then, of course, if you want to work on this, do some simulation, some computation, then it is even more. Typically, it could be in an explicit method that you have the same order. If the model creates a system of linear equation and you use Gaussian elimination, R would be 3 sitting here, for example. So the number of operations, and because you have to see all of these guys. So that is the challenge, that one cannot go ahead with a brute force method that covers everything if there is a large range of scales to deal with in this case. Mathematically, one sometimes can find these limits in the range that we had over there, going from molecular particle system all via a Boltzmann type equation to the continuum models from Navier-Stokes. That is not mathematically rigorously done. But for many other systems, you can do that. So you have the system that includes this epsilon scale, and you would like to see if mathematically in the limit where the scale separation and the scale range is extremely large, do this converge in some way, weakly or strongly, to a limit function, and is there a limit equation? And there are in many settings that is developed, like geometric optics. So if you here would like to do a rendering for a video sequence of some sort in this room, we would not use the wave equation in order to see how the light comes from the lamps over here to our faces. But we'll use geometric optics. So we wouldn't go in and bother about the wavelength here. We would just say that the light travel along straight lines in here, and that's the way it is done if you see the rendering in a computer game, for example, or animated movie. So this mathematical process that's developed, of course, in many other settings, and we will use homogenization as one example, where one gets influence from one of these asymptotic theories of classical type to how to do that numerically. So, if we don't have this effective equation, or the effective equation fails in some way, which then Navier-Stokes continuum model does precisely along the slip line in this case, or we could modify it but not from first principle, then we could actually do this computation locally, only in very small domain. And this would be sort of the framework here, that we will see if we can do sample small calculations and then use those in order to get information on the large scale. There are typically two different cases where you have this challenge. So if it is a too wide range of scales involved, and then you need to do local simulation. Two possibilities. One is that the local simulation is only needed in a very small part of the overall domain. Could be that you have a material where elasticity works well, but if you break it up at the crack tip, then you need to do something better. You need to use plasticity or go down to molecular level in this case. Or it could be that some component some phenomenon is missing everywhere, and you need to do something locally. So we have this composite material over here, for example, and you do not want to go down and do individual fibers everywhere on the surface, on this plate. So you could think about doing it before calculation, or you could do it on the fly, where you sample domains where you go down to the microscale. And that would be sort of our emphasis over here. So this framework here is of the type that you really would like to have this effective model, this effective equation, the geometrical optics, the homogenized model, or let's say Navier-Stokes instead of molecular dynamics. But there is something missing. It could be locally, the slip line, or it could be that you don't know the effective properties of this material. And what you do then is that there is some component here which you fill in, either by pre-computing or, that we mostly would do it during the calculation, from a microscale simulation that actually resolves the scale but only lives on small domains in doing that. And so you have to know the surrounding situation here. It's constrained to the setting that we have of the macroscale. And then you calculate the microscale, and that gives you whatever it would be that you need. It could be boundary information, or it could be some unknown quantity in some way. And that results in a method, in the best of all worlds, that works on the macroscale but has sort of the accuracy or incorporates ideas from the microscale. So that's the overall thing. And we started that with Owen Nunn in here, and that other people have developed it quite well for that. So there is some information theory that could support this type of approach in this basic setting of just representation of functions. And as we said in the beginning, Shannon tells us you have to have two unknowns per wavelength, 2 points per wavelength in order to represent a function at all. So that is sort of the minimum here. So now if we know a bit more, if we don't know anything more, then that's it. But we could know something more. For example, that you have a scaling law like this. This is typically what is done in singular perturbation and homogenization theory, averaging theory for dynamical systems, etc. So you assume that the solution has a smooth variation and then locally has a more oscillatory setting in this case. So this, you hope then, depending on the process of course, that in some way weakly or strongly it converges to some average or envelope or something like that. So it depends on the internal system. So if we don't know anything more, Shannon will tell you that we need to have this number of unknowns or points in the discretization. But if we know that it looks like that, then we can go a bit further, and we can first see that this function, if it is periodic in y, which was then x over epsilon, so that's why it oscillates, because of the periodicity there, then we can represent it as a Fourier series in the periodic variable, and a Fourier integral then in the coefficients over there. So that these coefficients are supported in a finite interval. Always in these information theory discussions, you have to assume band-limited functions. Otherwise, there is no limit. You cannot never represent it unless you do the full real line. But if it's band-limited, meaning that you discard higher frequencies or they are not there, then you can do this representation. And here we assume now that this function here is band-limited in both these variables. Here you get the support in this area, and this means that you can do a Fourier series. So the full function as a function of x, which now if we go back over here looks like this, just a function of x, would then have a support that looks like this. So this width here depends on the smooth part and the different bands here depends on jumping one to the other or the Fourier series to the point, the fast component. And then you have a sampling rate, which means how densely you need to put your points over here. A Nyquist rate is a sufficient condition. That is if you ignore the gaps, or if you ignore that it had a certain structure. And that would be of the order 1 over epsilon. The Landau rate is just sort of the number of unknowns on the physical side compared to the dual side, or the Fourier side. And this would not depend on epsilon in this case. It depends on the band limit of the individual functions. And so what one can show, we've done that with the students, Christina Frederick, that you can actually get a sampling that is optimal and stable and do the Landau rate. So you can do it as best as possible. And the sampling must be clustered in this way. You do not relate directly to the other cluster, but if you do this, then you resolve sort of the fast scale within the cluster and the slow scale with the variation between the two clusters. So there is some support that this way of doing localized simulation, if your unknown, wherever it comes from, has a structure that is typically done in these multiscale analysis problems. So the proof there is based that you use a Shannon construction, and then you miss out because it doesn't cover everything, and then you correct, and you do that literally, and you can from that set up then a Vandermonde problem, and you can use estimates for these matrices in order to show stability of that. Not ignore doing that, but it is not too complicated. But it's based on the original construction that Shannon used in order to do a full representation of a function in terms of the Fourier models. In total of the sample values in this case. So I'll take one example here, which is not practical, but the way of thinking. It tells a little bit how one would work. So let's say we would like to do the Euler equation in this case. And so we have conservation of mass, momentum, and energy. If you just use these conservation laws, you have too many unknown functions for equations. So you need to introduce a coupling here, an equation of states. And that is, of course, just an empirical law. It's not coming directly from first principles, but it's very good and used in gas dynamics, and you can fit it well with the appropriate choice of gamma. But let's say, for argument's sake, that we don't want to have this ad hoc law. We would like to do it more from first principle. We are interested in flow on another planet where we cannot go in and do experiments. But we know, for example, from spectrometry that what kind of molecules are involved. So the idea here, of course, is this is replacing the true thermodynamics that goes on in the fluid model. So why not do that from first principles? So we just do molecular dynamics in order to solve this problem. That's of course, it turns out to be costly if we do it everywhere. So let's see if we can use this principle. I go to one dimension here to it's easier to see. So here I have a conservation law, and the idea with the HMM, or the heterogeneous Multiscale method, is to try to do as much as possible on the core scale, on the macro scale, what you're interested in. So you discretize it. Let's say we do a finite volume method. Your averages would be the ones that are the unknown. So you have the average here as an unknown, you have the average up here. This is a time-space diagram. So if you do you just integrate this, and then you get a finite volume scheme. The new average of the quantities you're interested in is equal to the old average modulo the fluxes over the sides. And if you do numerical methods for this, what you typically do is, since you know the fluxes, you replace You don't know the individual values, but you replace them by a numerical flux, in this case. For example, the good enough method. So what you do is that you say, okay, in order to get the numerical flux over here, I take the average and call that the true value. So this will be piecewise constant, and I solve the Riemann problem over there, and then I can pick up the value that comes after the solution in here and stick that into the flux that I know. So this is one way of describing how it works. Okay, but I don't know the fluxes because I don't know the equations of state in this guy. I didn't want to rely upon that. I would like to do that in the more serious way. And then a possibility is just that I, at the location here, the state that I have of mass, momentum, and energy over here, just U, I start a molecular dynamics simulation locally and simulate for some time, as you do in molecular dynamics. It's sent down to a quasi-stationary setting, and then I measure the fluxes in the computer here. So for example, in order to do the mass flux, I just calculate how many of the molecules go from one side to the other and subtract on the other way. And then I have the fluxes, and I use that as my numerical flux and doing it. So that's sort of the way how it would look like in setting up that. So the gain in order to have this macroscale equation together with the simulation on the molecular level over here and put them together is, of course, that I only do the molecular dynamics when I need to evaluate the flux in this case. And that would be done in very small parts. That is only the size that is needed for any molecular dynamic simulation in that case. You can do that over here. And you can do that also if you kick this table over here for solid, where you instead would have a strain, velocity, and displacement, perhaps, and it could be in a nonlinear setting. You'll get also shocks in that setting. So you could do that, and there's a simulation there with the Jones potential for the microdomain. You have to run a number of them because you have statistical fluctuation around these things. So this is a possible way. It's not a practical way, but it sort of tells a little bit about the spirit, how you would do it in a setting like that. There are a number of issues, of course, that are swept under the carpet if we talk about it this way. And so one is how you do the estimation. If you go from the micro data to the macro model, here we just calculated the fluxes by counting it. It's a little bit harder with energy, but it's a well-established thing. The reconstruction technique, that I come back to a little bit later, that is not so obvious because the macro state had only mass, momentum, and energy, and then I'll replace that with a molecular dynamics simulation where there are thousands of degrees of freedom. So, so how do you put in the other guys in there? And you should constrain it to the right thing. So the number of molecules per unit volume should be given by the density. The average velocity of those guys should give you the velocity. The variation from the average should be given by the energy. The question is then, what will happen if I do the rest in a random, or maybe better than random, I use a Boltzmann distribution or something like that, Maxwellian. But you have then to rely on the problem. And here that's the same problem as molecular dynamics have in general. You have to have a system where the fast modes are slaved by these basic components. And it's, for example, it works very well in the air here, or in the water, in the cup over here, by just driving it with mass, momentum, and energy. If it's very rarefied, it's not enough. You know, there are different closure techniques in order to deal with that. And if it's even more rarefied, you have to go Boltzmann. So this depends on the situation where it's at. And then I'll let it go down here since I had it. And then you have boundary condition. Here they are artificial boundaries, but that's the same thing as you have whenever you do a local simulation, molecular dynamics or not. What are the conditions? Typically, if it is molecular dynamics, you do periodic boundaries, and then you drive it with some thermostat of some sort. Otherwise, you could have absorbing boundary conditions, or perfectly matched layers, or your favorite way of processing these guys. So these are issues. The question is, you could of course do a number of simulations and then determine the coefficients in the equational state before, and then use that. Or, as I said here, you do it whenever you need it. And we'll take one example later. Sometimes what one should do there is, when it's cheaper, to pre-compute and tabulate what it is, so we know how the pressure depends on the energy and the density. Then we could tabulate that function and use that. Sometimes it's cheaper to do it the way I described it. Do it on the fly, or concurrence, as you do it in all places like that. So that's a matter of computational cost. Here, scale separation is essential, and you don't have that always, like turbulence, because you need to be able to deal with a microscale in a domain that is much smaller than the size of the gridding in the macroscale. Otherwise, it doesn't pay you. So, therefore, that is. It actually does remarkably well even outside this, but in order to do any theory or any serious estimate, then you will do that. The problem where you have a localized problem and a crack tip, etc., then you don't need this, because you can just change the domain size. So this what was a finite volume method. If we think of a finite element setting, let's say we would like to do some problem, stationary problem, elliptic equation, come from whatever, some conductivity, heat distribution in a plate or something else. So a way to do that would be to discretize on a coarse grid that would represent the change of temperature in a gradual way all over the material. If it is a composite material, so we are thinking of this being varying the conductivity drastically on the microscale, and let's say we don't have a way of calculating the average, the property, then what to do? So one way is to first discretize on the coarse scale, then you start doing everything that you would do in a finite element discretization, including, let's say, quadrature of the stiffness matrix coefficient to get the stiffness matrix. But now you cannot evaluate it because you don't have the effective A's in there. That's when you go down and do a microscale simulation that resolves these epsilon scales, and you couple that to the macroscale. In this case, it would be the gradient of the macroscale. That is how this macro element, the P1 element, let's say, is tilted, should then be boundary condition for the microscale simulation, and then you can do that. And this you can handle. So this would be a finite element. If we take a dynamical system and we have some oscillations involved, it could be that you have some slow process, and then you have a stiff problem, and a stiff problem in the nature that it gives oscillation. If it dies out, the transient, dissipative part, it is easier, and you can use higher, that is localized, and you can use standard stiff solvers to do that. But if it is oscillatory, then the theory would tell you that the slow system can be seen by averaging over the invariant measure that is created by this process, and that is ergodic. So you solve that system over here, creating the set where V lives, and you integrate over that, and then you get this. So we'll try to mimic that in the same way. And the way to do that would be that you're given the initial state here, you would like to calculate over time, you would like to use large steps because that's where the slow part changes in the system. So what you can do is that you take a microscale simulation for a short time, you create the average force in the system, and you use that for your macro solver. So you have a running method over here, for example, and then you have another one over here, and then you do the average, and you come back, so you get this. And that is a localizing. In some problems for ODE, like the Fermi pasta Oolong thing, this procedure is the only way to handle that, as we know right now, to do something along those lines.
Bjorn, can I ask a question?
Yes.
Say, speaking about the previous example with the equation of states, so
Yes.
you suggested you replace it with molecular dynamics computation,
Yes,
right?
yeah.
For molecular dynamics, you need to know, say, the collision laws between particles, right? So
Yeah.
this suggests that perhaps
Yeah.
to do molecular dynamics on a smaller scale, on an even smaller scale, you would need to go quantum mechanics to derive cross sections, right? Or something like that. At some point, you need to decide, okay, here I am making an assumption, doing an
Yes,
approximation.
yes,
So any guidance as far as, like, where to stop or?
That's right. I mean, intellectually there is no limit in the sense that if we need, in order to do the forces, here of course it was empirical potential using Leonard-Jones in this case. So if you would like to do further, you would like to do something density function theory or even further to go down and use Schrödinger equation. Of course it's not practical, you have to, in that case, kick in the empirical, but go a little bit further. That is clear. It was more and this is what will be done in other cases also. But you're right. Sometimes first principle means somewhere on the way from looking at the nucleus to
It's like doing kinetic approximations. You take one particle, two particle, and then go.
yes, so
at some point you have
here, I will only talk about two stages, small and large scales here, but of course you can continue. So in order to do that, you could do the local simulation of this type here, in order to, in principle, of course it's costly, but in principle you could do that, so you could create the forces. And I have one example where this three-step thing was done, so that's in principle, you can do it hierarchically. So there is a challenge here, and that is how do you reinitialize? As I said, in the molecular dynamics, you were living, the system is so that the modes that are not represented by mass movement energy are slaved in, that they're dissipated, and those are the ones that live, and that's why we can use Navier-Stokes equation. But if you don't know anything, you take a dynamic system, then you have to rewrite it in a way so you can isolate the slope parameters, and then it doesn't matter how you initialize the rest. Those has to be initialized, and they are known because they are known when you march around here accurately, and the rest is not important. They just are there, and they wherever you start, if it's ergodic, it doesn't mean anything. You will after some time to create the same invariant measure. You can divide it up not just in slow and fast variable, but slow and fast processes. And if this is ergodic, then you can mix that also in the same way. So you need to know a little bit more. You could also add some dissipative part where you see which part of components are actually necessary to keep track of, or which are not important. Either they die out or they are ergodic. So wherever you start, you will get the same measure. So that's sort of where a lot of the theoretical work is going. The analysis here is very much like a standard analysis, getting convergence from stability and accuracy in a way. So what we had was the macro scale, missing data. You pick that up from the microscale that is calculated based on what state you are in for the macro variable, or for a subset of the micro variable. And that gives you a method together that essentially only deals with the macro scale. In order to do a theory, you have to be able to compare with something. And that is, the theory only works when you have an effective equation theory, like homogenization, geometrical optics, etc. And in that case, you then can discretize here for the full problems. You take this standard discretization, and you use the same discretization in both cases for the macro scale. So what you can do then is now compare the calculated heterogeneous multiscale method solution, HMM solution, with the true effective value. And then if you have stability of this method, which is the same as this, if you have stability over there, then the error in the calculation, it depends on the error in the microscale simulation, the error in the macroscale simulation, which is just regular numerical error, and the error in how you calculate this effective quantity from the microscale. How do you do the average? And that is, if we go back to this thing, it has to do with just doing the average force. You just sum them and divide with the number towards the error over there. And then rely upon the theory that exists over here, the theory there, what is the error in this process. So you have to calculate it. If you put it all together, then you get an estimate in the error over there. And you can prove convergence. So if you take the problem that we had over in the original setting, that's too ambitious. A nonlinear problem over there, and we cannot expect to go from particles to continue, because theory is not there. So let's say we are less ambitious. We take a linear flux function, heat flux. So f of u will be this. So you are solving a parabolic problem. So what the typical steps would be: you need stability and consistency on the microscale problem. You need that convergence of the computing microflux to the homogeneous flux. So there you need homogenization theory, that this flux here converges to a macroflux as epsilon over 0. And that has to do with the operator form, and then it also has to converge fast enough, that is an eigenvalue estimate, so that the convergence to this quasi-stationary state is in a short interval, so you don't cover the whole domain in this case. So that has to be fast enough to be compared to the discretization. And then the macroscale element has to be stable. And then you can put all these together, so you get convergence in a sense that is reasonable. If you do that. Of course, you would, in the convergence theory, you would let the macroscale go to 0, but you also have to be practical, not resolve the macroscale, otherwise it doesn't mean anything. It would be to solve the original problem. But you can do that in the theory that is reasonable. So we've done a number of applications with different people. So this could, for example, be crack tip, where you only do a detailed simulation locally. This is thermal expansion, which is very much like the example we had with the Euler equation. But of course, thermal here. This was a slip line over in this setting. These are different thermal studied, and this is a chip over there where you are interested in the heat distribution if you use in the chip. This is epitaxial growth, detonation front, where the chemistry is much faster than the fluid dynamics, if you do that. And these are mechanical systems where you have ODs for the different components, where you have fast springs and slow springs to study the phenomenon in this case. So let's start with the finite HMM method, where this is a coupling, and most of that was done there the coupling is over here, and you're looking at composite materials, where it may not be periodic, it could be some other geometric structure you're interested in, but you still do sampling locally and do the calculation and put together precisely as over here, even in the setting there. And he's done a number of things with disc brakes and the heat conduction over there. These are done by composite materials and put it in. In order to make it faster, you also use reduced basis simulation, so that the microscale calculation is more efficient. So it's somewhere in between doing pre-calculations. You do pre-calculations in order to get a good basis by different samples, and then on the fly calculation, where you have then done these pre-calculations, or the snapshots, as they call it in this business. And the process will then be very similar to what I described before in this, but you gain in efficiency by doing reducing the basis for the microscale that you're doing. So this worked in fairly good calculation. If you go back to this guy and take a simulation that we did over there, so simplified, and this is just 2D, so you have one invisible fluid, one on one side of the red line, the interface, and one of the others, and these are solid. So you have three types of atoms or molecules in this setting, the solids and the two fluids. So what you do is that you do Navier-Stokes everywhere with no slip condition, but for these particular points where you go down and do a molecular dynamic simulation with the heat bath in order to force the velocity on the top coming from the interior, and then you would get the shear stress and the fluid, the line velocity back from the microscale simulation, which you feed into the Navier-Stokes simulation. And you have the force from the fluid into this microscale box that you're doing. And then you can read off along this line where the velocity is. And if you're away here from the interface, then the molecules sit still in the molecular dynamic simulation. And when you come closer to this, then the forces from this triple point here is strong enough in order to push the molecules along the boundary, and you get something that the stress is a derivative of this, so it's more noisy, which you feed back in. So it's possible to do this. Of course, in practice, I wouldn't say that. Oops. Wow. So, I didn't want to go in that anymore. Now it starts the clock all over again, so I can have a much longer. I don't know whether it was something over there or whether it was just Microsoft not doing its job. That's much further than this. Oops. We do another thing.
If you have a PDF version, I'd probably say open the PDF. It looks like the Microsoft.
I wonder what, I'll see here. I'll do the one more here and go past this. Well, I can't do that. Is there some way you go directly? No, it is not. Yeah, I have a PDF version. I did that on the stick. Let me just see whether it's. Can I jump further? Somewhere here, probably not. You get to see this part at least. So it was it was the next one, was it? Oh no, this result. And this result. And this is the next one. Okay. Next problem here. We'll see what happens. Sorry about that. So this is epitaxial growth. So this is in semiconductor manufacturing. This is more realistic. This was actually used, and the heat conduction was also used. But this has practical value. So the process over there is that you would like to create very thin films of one material. So you deposit atoms of a certain type on the substrate, silicon, and you would like to do just a few layers, 20, 50 or so. And you can do that by depositing atoms here in an enormous vacuum, and then have heat, so they move around and they stick together, and then the probability of moving away is smaller, and they jump otherwise around, and they form these islands that grow, and then next layer starts on top of that. So this is the process here that is used. And the problem in the simulation here is that the substrate is quite large, so it is a bit too ambitious to be on the molecular level over here. So, so one other technique is to use kinetic Monte Carlo to simplify. So this is also simpler than doing the true molecular simulation, but that is what people use in over here. So this would be on the microscale one. In order to tune the kinetic Monte Carlo, then you could do a density function theory, for example. So this was done in a 3-step, but that was done pre-computing. So you got the probabilities of jumping from a DFT simulation, or jumping from the boundary in inside here, which are a little bit different, or from the top to the bottom, from the bottom to top, etc. So they were done, and once that is done, you can do kinetic Monte Carlo. That's too expensive. So you would like, for example, just to use diffusion out in this domain, and on top over here. So where you really need the molecular thing is on the boundary here, around there, because the roughness of the boundary, how it was developed, tells how much they stick, and it tells how fast it grows. So what you're needing is you would like to do this simulation on a macro scale, diffusion, and the boundaries are represented here by level set, and you see how that grows. So layer after layer you increase and do that. So the idea is to sample here and use kinetic Monte Carlo in order to see the growth. So you take a particular individual sample and you go down to the atomistic level, and you evolve it by Monte Carlo random sampling, and see how this guy moves, how it sticks, the probability that it leaves, etc. And that you simulate, and then you see how this front here grows. First, how it develops roughness, and once it's settled, then you can measure the growth, the velocity in the normal direction, and feed it back to the macroscale simulation. And that worked pretty well, and you can then do comparisons with experiments, or you could do a comparison on full Monte Carlo if you're in a small channel and there's a number of steps, and see accurately. Here you cannot do any theory for it. So that is a possibility of going between a macro and multiscale. It's an interesting thing here. How much do I need to know about the effective equation when I do a simulation like that? So let's say wave propagation over here. So this will be the wave equation. And let's say you have wave propagation in the composite material here, the easiest one with a microscale to deal with. So here you have the blue points over here would be the macro step. And in order to do that, I need to evaluate this flux term, if you call it like that, this guy, that you don't know, but I need to do that, and I do that by microscale simulation over there. And if I do that, what would happen is that I can get, even if the individual pieces are isotropic, I can get an anisotropic if there's a layered material. I get different velocities in different layers, for example. So all of that is. But I get something that is on this particular form. It is a heat equation with constant coefficient. Sorry, a wave equation with constant coefficient from this variable coefficient. So if you do that and you run it for a long time, then it actually happens that the solution satisfies an equation where there are correction terms. So I will run it for a time that depends on epsilon here, the distance between the layers, if there are layers. Then there is a dispersion effect that comes in over here, and that's real. So the question is, I didn't know that from the beginning, actually in principle, and in this case it wasn't, I should have known. Then does it work anyway? And it does. So the simulation, the simulation here was done just with a straightforward simulation. You need to be more accurate locally, higher order approximation, and do better interpolation when you restart the value. But if you do that, then you can simulate for a long time, and you get actually a solution that includes the dispersive effect that is not coming out of the standard homogenization theory. What was done in turbulence setting, that was one case where I said you had difficulty, there was no scale separation. you have all things. But there is some scale balance, at least if you do atmospheric flow, because the atmosphere is very, very thin, and the important forces in, let's say, the turbulent transport in clouds is on a much scale that is very separated from whatever is the vertical changes in pressures, when the low pressure regime comes and velocity changes. So therefore, in de facto, even if it's not so in theory, you have these separate scales that carry most of the energy in this case. And this was done actually independent of our development here by the group at NCAR in those days, National Center for Atmospheric Research. Grabowski was the one starting it, and it's continued. And the idea is that you do a discretization on a core scale, as they usually do for climate or a meteorological case, and then locally, in order to, instead of having coefficients about the diffusivity or the turbulent transport, that's usually done by measured coefficient, but you can do a local simulation, just sort of chop out a small component of the atmosphere and do a simulation. And actually they go even further, and they even don't do a 3D simulation, but a 2D simulation, or two 2D simulations together, and get them better fit to the overall flow in this case. So, and this is of course in the same spirit as before. You end up with a Texas problem, so this is flow in porous medium, oil reservoir modeling in this case. So you have typically Darcy law will be the macroscale formulation. So this is a function, we take the gradient of a function depending on pressure. So typically an elliptic equation in the pressure that gives the pressure, and then you can use that to drive the velocity. The Darcy law assumption is that the velocity field that is proportional to the pressure gradient. That's the assumption. So you don't need the inertia term is gone, etc. Of course, the porous media is not homogeneous, and this is there. So the effect that is gathered in the macroscale equation comes from the flow that is squeezed around particles in the sand and soil and shale or whatever you have. And one way in between, again, there we are not going back to the original, first principle thing, is to use a network model. So you think of pipes connecting the voids in over here. And that is usually known, particularly if you have multi-phase flow, as a good model to do that. And we use that as a microscale model. And then you have a finite volume method for the Darcy law with unknown flux or permeability property, and you get on the fly the permeability properties from simulation of this type. You could also do that, so you could actually look at the fracture chain. So you can couple it to a fracture model, and then in the microscale simulation you would have the fracture development from the pressure that is known, the flow changes, the pressure changes, and then you correct for that. So you go in a loop where you couple local fracture simulation in a network model, how this network breaks up due to the pressure that comes in, and that is the process of hydraulic fracturing. And then you couple that to the whole model. Of course, this is very synthetic in this case, but it certainly is a possibility, and in order to do that, and that's it. So the idea is that classical mathematics, particularly asymptotic techniques, and also in rigorous type of techniques, it can sort of be coupling different models or looking at the limit equations or effective equations. It can be used as sort of a modeling source in doing that. And that means that the possibility is to use first principle in a little bit wider range of problems that we're doing. Whenever there is an established theory, then one can have rigorous convergence proof that makes sense. In most practical cases where one doesn't have that, so one has to experiment and get some physically realistic result comparing with the real world. That's it. Thank you.
Questions?
I'll
Yes.
ask another one. Say, getting back to that highly dynamic example, or Euler's equation example, is there any guarantee with this multi-scale approach that, for example, you won't break the second law of thermodynamics, so the H theorem, does it sit someplace there? I mean, with like, with the conventional equation of state, well, I mean, okay, maybe sort of an approximation, but at least it guarantees that nothing will go wrong along those lines. So when you are replacing it with something computed,
Yes.
especially as you compute on the go, when you say so.
Yes. Well, I have not done that, of course. But in a sense, what you would do. So the question is, would you sort of leave the structure that was there in the original hyperbolic problem by doing this, getting certainly if you calculate, use it to calculate equations of state by local simulation for the particular values and feed it in, then it would not be, then you would just compute another equations of state, maybe good or bad, and then you would be back in the same situation. If you just feed in instead of going via a equation of state by directly doing the fluxes of mass, momentum, energy, if you would have a possibility of losing, I haven't thought about that, but it's yeah, doubt it because it's so highly coupled to the other one. But yeah, that should be proving something. One has to go via H theorems and have a simplified version instead of that, doing some Boltzmann type thing.
Thank you.
Other questions? I also have a question about this. You mentioned this reconstruction between micro and macro.
Yes.
So I guess it's done deterministically, right? So
Yes.
did anybody consider, or would it make sense to do some stochastic approach, like non-parametric estimations, things?
Yeah, I mean the stochastic part here was done in the MD simulation. That the distribution of the velocities of the part and the location of the original molecules in that case was done by random distribution of using sort of following Maxwellian all the stationary situation. So in that sense, it was used over there. The other setting was where stochastic features that come in was in the dynamical system, and that was not on a realistic thing, but just studying a model where you have a slow mode, it's an ODE. The fast mode is an SDE, a stochastic differential equation, where there is a drift and where there is some Brownian motion source feeding into this thing. And if it's clean enough, you can also do theory on that one. The other one, there is no theory that guarantees that a certain distribution will, for such a difficult particle system, that it will actually converge. So there is just practice that is in the theory. But for the dynamical system, then you can use similar theories that are used in Monte Carlo simulation.